Imagine this for a moment. Two identical clocks are built with absolute perfection. They tick at exactly the same rhythm, down to the smallest fraction of a second. One clock stays with you on Earth. The other is taken far into space, placed on a satellite orbiting high above the planet. A few days later, when we compare them, something impossible has happened. The clocks no longer agree. One has aged more than the other. No malfunction, no trick, just gravity. Now let me ask you something even stranger. If you stand on the floor right now, your feet are aging more slowly than your head. The difference is incredibly tiny, far too small to notice, but it is real, measurable and proven. Time itself is flowing at different speeds across your own body. This is not philosophy, this is physics. And it all begins with gravitation. For centuries, we believed time was absolute. One universal river flowing at the same rate everywhere in the universe. A second was a second, no matter where you were or how fast you moved. Gravity in that worldview was simply a force that pulled objects together. It made apples fall, planets orbit, and tides rise and fall. Time and gravity were separate ideas, living in different compartments of physics. But nature had a far deeper story to tell, one that would completely change our understanding of reality. Before we reach black holes, warped space-time, and clocks that slow down near massive objects, we must start with something deceptively simple: a swinging pendulum, a child's clock, a motion so familiar that we rarely stop to think about what truly controls it. Why does a pendulum swing at a particular rhythm? Why does it take a fixed amount of time to complete one oscillation? Why does that time change when you climb a mountain, travel to another planet, or move closer to the center of Earth? This is the story of the time period in gravitation, a journey that begins with classical mechanics and quietly leads us to the edge of cosmic time itself. The idea of a time period seems straightforward. It is simply the time required for a motion to repeat itself. One full swing of a pendulum, one complete orbit of a planet, one revolution of a satellite around Earth. But hidden inside this simple definition is a powerful truth. Every repeating motion in the universe is governed by gravity. Change gravity, and you change time. Long before Einstein bent time itself, Galileo Galilei stood in a cathedral, watching a chandelier swing back and forth. But he noticed something remarkable. Whether the swing was wide or narrow, the time it took to complete one oscillation remained nearly the same. This observation would eventually lead to the pendulum clock, humanity's first truly accurate timekeeping device. But Galileo didn't know why this happened. He only knew that gravity was somehow setting the rhythm. Later, Isaac Newton would give us the mathematical language to describe this rhythm. Gravity, according to Newton, was a force acting instantaneously across space. The stronger the gravitational pull, the faster objects accelerated and the quicker oscillations occurred. In this framework, time itself was untouched, absolute, universal, and unchanging. Gravity influenced motion through time, but not time itself. And for everyday experiences, this picture worked beautifully. A pendulum's time period depended on only two things: its length and the strength of gravity, not its mass. Not the material it was made of, just length and gravity. On Earth, this gives us a predictable rhythm. But what happens if we change the strength of gravity? What happens if the same pendulum swings on the Moon, where gravity is weaker, or on Jupiter, where gravity is far stronger? The answer is astonishingly simple and deeply revealing. The pendulum slows down where gravity is weaker. It speeds up where gravity is stronger. Time, as measured by motion, stretches and compresses depending on gravitational strength. Even in classical physics, gravity is already shaping how time is measured. But this is just the surface. As humans climbed mountains and sent instruments higher into the sky, tiny discrepancies began to appear. Pendulum clocks at higher altitudes ticked slightly slower. The difference was minuscule but persistent. Gravity weakens with height, and the time period responds. The rhythm of time subtly changes with location. At first, this was just a curiosity, but then we began to place clocks in orbit. Satellites circling Earth move fast and experience weaker gravity than objects on the surface. According to Newtonian mechanics, their orbital time periods could be calculated with incredible precision. And yet, when engineers compared satellite clocks with ground-based clocks, something unexpected happened. The difference was too large to ignore. Newton's gravity could predict motion, but it could not fully explain the behavior of time. This was the moment Einstein had anticipated decades earlier. Einstein proposed something radical. Gravity is not a force pulling on objects through space. Gravity is the curvature of space-time itself. Massive objects like Earth don't just attract things, they reshape the geometry of time and space around them. And when space-time curves, time does not flow at the same rate everywhere. Closer to a massive object, time runs slower. This idea is not metaphorical, it is literal. Atomic clocks placed at different heights tick at different rates. GPS satellites must correct their clocks every single day because time in orbit flows faster than time on Earth's surface. Without accounting for gravitational time dilation, your phone's navigation system would drift by kilometers within hours. On what began as a simple question about the time period of a pendulum now reaches into the infrastructure of modern civilization. But the story does not stop there. If gravity can slow time slightly near Earth, what happens near something far more massive? A neutron star, where gravity is billions of times stronger than Earth's? Or a black hole, where gravity becomes so intense that time itself appears to freeze? Near a black hole, the concept of a time period becomes almost meaningless. An orbit can still exist, but to an outside observer, the clock of an object falling toward the event horizon slows down endlessly. The motion continues, but time stretches toward infinity. The time period, once a simple measure of repetition, now depends on who is observing and from where. This is the ultimate lesson of gravitation and time. There is no single universal clock for the universe. Every object carries its own time, shaped by gravity and motion. And yet, here we are, living our daily lives, unaware that time is not flowing uniformly, even across the surface of our planet. Your past self, standing at sea level, aged slightly slower than you do right now if you are at a higher altitude. Astronauts aboard the International Space Station return to Earth having aged a tiny bit less than the rest of us. The universe quietly allows time travel into the future, one gravitational field at a time. In this video, we are going to unpack this entire journey carefully and clearly. We will start with the classical understanding of time period under gravity, pendulums, oscillations, and orbital motion. We will explore how gravity changes with location, height, and depth, and how those changes affect timekeeping. Then we will move beyond Newton and step into Einstein's universe, where gravity bends time itself. Finally, we will push to the extremes: neutron stars, black holes, and the ultimate limits of time under gravitation. By the end, you will see the time period not as a dry formula, but as a window into how the universe measures existence. You will understand why gravity is not just the architect of motion, but the sculptor of time itself. So before we dive into equations, experiments, and cosmic phenomena, keep this thought in mind. Every second you experience is shaped by gravity. The rhythm of your life is set by the mass beneath your feet and the curvature of space-time around you. Time is not ticking independently in the background. It is responding moment by moment to the gravitational universe you live in. When we talk about the time period in gravitation, the most natural place to begin is with motion that repeats itself in a simple, almost hypnotic way. A pendulum swinging back and forth. At first glance, it feels too ordinary to carry deep cosmic meaning. And yet, hidden inside that gentle oscillation is one of the most profound relationships between time and gravity ever discovered. Imagine suspending a small metal bob from a string and pulling it slightly to one side. You release it and it begins to swing. Back and forth, left to right. Each complete swing takes a fixed amount of time. That time is what we call the time period. What is astonishing is how stubbornly consistent this time period is. Change the mass of the bob and nothing happens. Use iron instead of wood, and nothing happens. Make the bob heavier, lighter, denser, or hollow, the rhythm stays the same. Nature is telling us something very clearly here. The time period of a pendulum does not care about matter. It cares about gravity. Mathematically, this relationship is beautifully simple. The time period depends only on the length of the pendulum and the gravitational acceleration of the place where it is swinging. Gravity is acting as a timekeeper. Stronger gravity pulls the pendulum back faster, shortening the time period. Weaker gravity allows it to drift more slowly, stretching time. This is not a philosophical idea, it is measurable. Take the same pendulum to the moon, where gravity is about 1/6 of Earth's. The swing slows dramatically. The seconds lengthen. A clock built on Earth would fail completely on the moon. It would lose time not because it is broken, but because gravity itself is weaker. This simple observation already breaks an intuitive belief many people hold, that time is universal and independent of environment. Even in classical mechanics, time as measured by physical processes is shaped by gravitational conditions. When Galileo noticed the near-constant period of a pendulum, he unknowingly discovered a natural clock governed by Earth's gravity. Newton later explained this using his laws of motion and gravitation. Gravity provides the restoring force that pulls the pendulum back toward equilibrium. The stronger that force, the faster the motion, and the shorter the time period. Now imagine taking this pendulum experiment and moving it to different locations on Earth. Not different planets, just different places. At sea level, Gravity has a certain strength. On top of a high mountain, gravity is slightly weaker because you are farther from Earth's center. The difference is tiny, but it exists. And because the time period depends on gravity, the pendulum on the mountain swings a little slower. Over the course of a day, a clock at higher altitude loses time compared to one at sea level. This is not theoretical. It has been tested repeatedly. Gravity is not uniform across Earth, and timekeeping responds accordingly. Earth itself complicates the story further because it is not a perfect sphere and it is rotating. At the equator, the planet bulges outward slightly, and rotation produces a centrifugal effect that reduces effective gravity. At the poles, gravity is stronger. As a result, a pendulum clock ticks more slowly at the equator than at the poles. Two identical clocks, perfectly synchronized, will slowly drift apart simply because of where they are placed on Earth. This reveals something crucial. Even before relativity, gravity already introduces local time differences through motion. Now let's take a step deeper and consider a thought experiment that pushes this idea to its limit within classical physics. Imagine drilling a tunnel straight through Earth, passing through its center and emerging on the opposite side. Now imagine dropping a small object into this tunnel. What happens? According to Newtonian gravity, the object does not fall endlessly faster. Instead, it undergoes simple harmonic motion, oscillating back and forth through Earth's center. Remarkably, the time period of this motion does not depend on how deep the tunnel is or where you drop the object from. Or it depends only on Earth's density. The object completes one full oscillation in about 84 minutes. This result is stunning. Gravity inside Earth creates a natural clock, one that is independent of amplitude and distance. Even buried deep within a planet, gravity still sets a precise rhythm for time. What these examples teach us is that time period in classical gravitation is fundamentally about how gravity controls acceleration. Whether it is a pendulum, a falling object, or an oscillation through Earth, gravity defines how quickly motion unfolds. Time, in this framework, is still absolute in theory, but in practice, it is always measured through motion. And motion answers to gravity. This brings us naturally to orbital motion, where the idea of time period expands from swinging objects to celestial mechanics. Planets orbit stars. Moons orbit planets. Satellites orbit Earth. Each of these motions has a time period, and each is governed by gravity. Johannes Kepler discovered, through careful observation, that planets farther from the Sun take longer to complete their orbits. Isaac Newton later explained why. The gravitational pull weakens with distance, and weaker gravity means slower orbital motion and longer periods. The relationship is precise and universal. Square the orbital time period, and it becomes proportional to the cube of the orbital radius. This simple law governs everything from artificial satellites to distant exoplanets. A satellite close to Earth races around the planet in roughly 90 minutes. A geostationary satellite, much farther away, takes exactly 24 hours, matching Earth's rotation. Gravity sets the pace. Change the altitude, and you change the time period. At this point, everything still fits comfortably within Newton's universe. Time flows the same everywhere. Gravity influences motion, not time itself. But cracks begin to appear when we demand extreme precision. When engineers began placing highly accurate atomic clocks aboard satellites, they noticed something troubling. Even after accounting for orbital mechanics, satellite clocks did not stay synchronized with clocks on Earth. The difference was small, but it grew steadily. Something beyond classical gravity was at work. This realization marks the transition to the second major part of our journey, where gravity stops being just a force and becomes something far more profound. To understand what happens next, we must let go of the idea that time is merely a background parameter ticking uniformly for the entire universe. Einstein asked a simple but radical question: what if gravity affects time itself? According to Einstein's general theory of relativity, gravity is not a force in the traditional sense. It is the curvature of space-time caused by mass and energy. Massive objects like Earth distort the geometry of space and time around them. Objects move the way they do because they are following the curved paths of space-time. And crucially, clocks tick differently depending on how curved space-time is where they are located. This leads to gravitational time dilation. A clock closer to a massive object runs slower than a clock farther away. The effect is tiny near Earth, but it is real. Atomic clocks placed at different heights confirm this prediction. A clock at the top of a building ticks slightly faster than one at the ground floor. The difference is measured in billionths of a second, but it accumulates over time. Now return to our discussion of time periods. When gravity affects the rate at which time flows, it also affects every periodic process. Every oscillation, every vibration, every orbit becomes observer-dependent. The time period is no longer a universal quantity. It depends on gravitational potential. Consider a pendulum clock on Earth's surface and an identical clock placed on a satellite in orbit. From the satellite's perspective, the Earth clock is running slow. From Earth's perspective, the satellite clock is running fast due to weaker gravity, but slow due to high speed. But the final result is a precise combination of gravitational and relativistic effects. Engineers must correct for both. If they did not, GPS systems would fail catastrophically. Your phone would think you are kilometers away from your true location within minutes. This is where the concept of time period evolves from classical to relativistic. In Newtonian physics, time period changes because motion changes. In relativity, motion changes because time itself changes. Gravity no longer just controls acceleration, it controls the flow of time. The deeper you go into a gravitational well, the slower time passes. Near a neutron star, where gravity is immense, a second for you would be many seconds for a distant observer. Near a black hole, the effect becomes extreme. As an object approaches the event horizon, its clock appears to slow down endlessly from the perspective of someone far away. The time period of any motion, any orbit, any vibration, stretches toward infinity. Motion continues locally, but time, as seen from afar, nearly stops. This does not mean time truly stops for the falling object. Locally, everything feels normal. The pendulum still swings, the heart still beats, but the connection between observers breaks down. There is no single shared time period that everyone can agree on. Gravity has shattered the idea of universal time. And this brings us back to the central theme of this entire discussion. The time period in gravitation is not just a formula learned in physics class. It is a gateway concept. It begins with pendulums and orbits. but it leads directly to the realization that time itself is shaped by the structure of the universe. Gravity does not merely influence how things move through time, it defines how time flows in the first place. As we continue further, we will push these ideas to their extremes, exploring cosmic objects where gravity dominates completely and time behaves in ways that challenge human intuition. But even now, standing on Earth, every second you experience is already being sculpted by gravity. The rhythm of your existence is not universal. It is local, shaped by the mass beneath you and the curvature of space-time around you. As we push deeper into the gravitational story of time, we now leave behind familiar environments like Earth and its satellites and move toward regions where gravity is no longer gentle or forgiving. Up to this point, gravity has subtly stretched and compressed time, producing effects small enough that we need atomic clocks to notice them. But the laws governing these effects do not suddenly change just because gravity becomes stronger. They intensify, and when gravity intensifies, the very idea of a well-defined time period begins to bend, blur, and eventually lose its classical meaning altogether. Imagine an object orbiting a neutron star. A neutron star is the collapsed core of a massive star, packing more mass than the Sun into a sphere barely 20 kilometers wide. Gravity there is so intense that a teaspoon of its matter would weigh billions of tons on Earth. Near such an object, space-time is severely curved. The orbital motion still exists. Objects can still circle the star. There is still a repeating motion, and therefore a time period. But this time period is no longer something that all observers agree upon. From the perspective of an astronaut orbiting the neutron star, everything seems normal. Their clock ticks steadily. The orbit completes in a certain amount of time. The laws of physics feel intact. But from the perspective of a distant observer far away from the neutron star, something extraordinary happens. The astronaut's clock appears to run slower. The orbital motion appears stretched in time. One revolution takes longer than it should. The stronger the gravity, the greater the discrepancy. Time itself is being pulled apart. This is one of the deepest lessons of general relativity. Time period is not an intrinsic property of motion alone. It is a relationship between motion, gravity, and the observer. Two observers in different gravitational fields will measure different time periods for the same physical process, and both measurements are correct within their own frames of reference. Now imagine moving even closer to the ultimate gravitational boundary, a black hole. As an object approaches the event horizon, gravity becomes so extreme that space-time is warped beyond anything encountered elsewhere in the universe. To the falling object, time continues to flow normally. Its internal processes proceed without disruption. But to an observer far away, the object's clock slows down dramatically. The time period of any repeating motion stretches longer and longer. A heartbeat takes seconds, then minutes, then hours. From the outside, the object never quite crosses the event horizon. Time seems to freeze. This is not because motion stops, but because time itself is being distorted by gravity. Near a black hole, the idea of a fixed time period becomes observer-dependent to an extreme degree. There is no universal answer to how long an orbit takes or how long a vibration lasts. The answer depends entirely on where you are standing in the gravitational landscape. And yet, within this chaos, the laws remain consistent. Gravity does not randomly alter time. It reshapes space-time in a precise, predictable way. The deeper the gravitational well, the slower the passage of time relative to distant regions. This principle applies everywhere, from Earth to the edge of a black hole. The difference is not in kind, but in scale. Now let's step back from these cosmic extremes and return to a more subtle but equally profound question. Why don't we feel these effects in everyday life? Why does time seem to flow smoothly and uniformly for us, despite the fact that gravity is constantly shaping it? The answer lies in scale and perception. On Earth, the gravitational differences across our daily environment are extremely small. The difference in gravitational potential between your head and your feet is tiny. The resulting time dilation is measured in billionths of a second. Your biological processes, your thoughts and your senses are far too slow to detect such differences. To you, time feels uniform, but nature does not care about human perception. It operates with absolute precision, whether or not we notice. This leads us to one of the most important realizations in modern physics. Time is not a universal backdrop against which events unfold. It is an active participant in the dynamics of the universe. Gravity shapes time and time shapes motion. The time period of any process is therefore not just a property of the system itself, but of its position in space-time. Now consider how this understanding reshapes our view of the universe on the largest scales. Planets orbit stars. Stars orbit galactic centers. Galaxies move through clusters. Each of these motions has a characteristic time period. But the gravitational environment of each system is different. Time flows slightly differently in the deep gravitational wells of galaxies than it does in the vast emptiness of intergalactic space. Over billions of years, these differences accumulate, subtly influencing cosmic evolution. Even the expansion of the universe itself is tied to the flow of time. So in regions of strong gravity, time slows, affecting how processes unfold locally. In regions of weak gravity, time flows faster. The universe does not age uniformly everywhere. Different regions experience the passage of cosmic time at different rates. This is not speculation. It is a direct consequence of the gravitational nature of time. As we approach the final part of this exploration, we confront a philosophical shift that gravity forces upon us. In classical physics, time period was a clean, objective quantity. Measure it once and everyone agrees. In relativistic physics, time period becomes relational. It depends on who measures it, where they are, and how gravity shapes their space-time. This does not make physics subjective, it makes it deeper. Every clock is honest, every measurement is valid, but no single clock tells the whole story. This realization changes how we think about aging, causality, and the structure of reality itself. Astronauts returning from space are measurably younger than their counterparts on Earth, not because of science fiction, but because gravity and motion have altered their personal flow of time. In extreme gravitational environments, this effect becomes dramatic. Time travel into the future is not only possible, it is already happening. Now let us tie this cosmic perspective back to the original idea of time period. Whether it is a pendulum, a satellite, a pulsar, or a particle orbiting a black hole, the time period is always a dialogue between gravity and motion. In weak gravity, this dialogue is quiet and almost invisible. In strong gravity, it becomes deafening, reshaping our understanding of reality. As gravity increases, classical descriptions of time period lose their simplicity. Near a black hole, even defining a stable orbit becomes difficult. Certain orbits simply cannot exist. Light itself can orbit only at a specific radius, and even then, the concept of a repeating path is fragile. Time stretches, paths twist, and the distinction between space and time begins to blur. This is where gravitation teaches us its final lesson. Time is not something that exists independently of the universe. It is woven into the fabric of space-time, shaped by mass and energy. The time period of any process is therefore not a fundamental constant, but an emergent property of the gravitational environment. When we look back at the humble pendulum, we now see it differently. Its steady swing is not just a mechanical motion. It is gravity whispering its influence on time. When we look at planetary orbits, we see gravity conducting a cosmic symphony, setting rhythms that span years and centuries. When we look at black holes, we see gravity rewriting the rules entirely, pushing time toward its limits. And through it all, one truth remains constant: gravity and time are inseparable. To understand one, you must understand the other. By following the thread of time period through gravitation, we have traced a path from everyday experience to the edge of the known universe. We have seen how gravity shapes motion, how motion reveals time, and how time itself bends under the weight of mass. This journey does not end with equations or experiments. It ends with a changed perspective. And the next time you glance at a clock, remember that it is not merely measuring time. It is responding to gravity. It is participating in the curvature of space-time. Every tick is a negotiation between mass, motion, and the geometry of the universe. In the final moments of this exploration, what remains is not just knowledge, but awe. Awe that something as familiar as time is so deeply connected to something as powerful as gravity. Awe that the universe allows such elegant laws to govern both the swing of a pendulum and the dance of galaxies. And awe that, by understanding the time period in gravitation, we glimpse the hidden rhythm that underlies all of existence. As we move further into this journey, the discussion of time period in gravitation now reaches a stage where theory, observation, and technology intersect. Yet until now, we have explored how gravity shapes time in principle. From pendulums to planets, from satellites to black holes. Now we turn to the living proof of these ideas. Places where gravitational time effects are not just theoretical predictions, but practical necessities. This is where gravity's influence on time period becomes unavoidable, measurable, and essential for modern civilization. Consider pulsars, one of the most extraordinary objects in the universe. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse, producing pulses that reach Earth with astonishing regularity. Some pulsars rotate hundreds of times per second, making them among the most precise natural clocks ever discovered. more stable than many atomic clocks on Earth. At first glance, pulsars seem to reinforce the idea of absolute time. Their pulses arrive with such consistency that astronomers can predict them years in advance. But gravity is still at work here, quietly shaping what we observe. Pulsars exist in regions of extremely strong gravity. Time near their surfaces flows much more slowly than it does for us. The reason their pulses appear stable is not because time is universal, but because the pulsar's own internal processes are governed by its local spacetime. The time period of its rotation is defined within its gravitational environment. When we observe it from Earth, we are seeing a time signal that has already been shaped by intense gravitational time dilation. In binary pulsar systems, where two neutron stars orbit each other, the effect becomes even more profound. These systems lose energy over time, not through friction or resistance, but through the emission of gravitational waves, ripples in space-time itself. As energy is lost, the orbital period changes. The time period of the system slowly decreases, exactly as predicted by Einstein's equations. This was one of the first direct confirmations that gravity is not merely a force, but a dynamic structure that can carry energy and affect time-dependent motion. Here, the time period is no longer just a measure of motion. It becomes a diagnostic tool. By studying how orbital periods change, scientists can infer the strength of gravity, the curvature of space-time, and even the existence of phenomena that cannot be seen directly. Your time period becomes a messenger from the depths of gravity. Now bring this idea back closer to home. The most powerful demonstration of gravitational time effects in everyday life is the Global Positioning System. GPS satellites orbit Earth at high altitudes and high speeds. Each satellite carries atomic clocks that are incredibly precise. But if these clocks were allowed to tick without correction, the entire system would fail. Why? Because gravity and motion are altering their time periods relative to clocks on Earth. Due to weaker gravity at orbital altitude, satellite clocks tick faster than clocks on the ground. Due to their high speed, special relativity causes them to tick slower. When these two effects are combined, the net result is that satellite clocks gain about 38 microseconds per day relative to Earth clocks. This may sound insignificant, but over the course of a single day, this discrepancy would translate into navigation errors of several kilometers. To prevent this, engineers deliberately adjust the satellite clocks before launch. The time period of the atomic transitions used in these clocks is modified so that once in orbit, they tick in perfect synchrony with Earth-based timekeeping. This is gravity shaping time at a technological level. Without an understanding of gravitational time dilation, modern navigation, aviation, and global communications would be impossible. What makes this so remarkable is that the same principle governs everything from a pendulum to a satellite to a pulsar. Gravity determines how time unfolds locally, and the time period of any process reflects that local gravitational environment. But the difference is scale, not nature. Now let us go one step further and confront one of the most subtle and profound consequences of this idea: the relativity of simultaneity and its impact on time periods. In a universe where gravity curves space-time, different observers do not agree on what events are simultaneous. This means that even defining the start and end of a cycle, a single time period, can depend on the observer. Imagine two identical clocks placed at different heights in a gravitational field. From your perspective, standing somewhere in between, they tick at different rates. But from the perspective of one of the clocks, the other appears distorted in time. There is no single universal reference frame that can declare which clock is truly right. This does not mean physics is uncertain. It means that time itself is local. This local nature of time leads us to a deeper understanding of causality. In classical physics, cause and effect unfold within a single timeline shared by the entire universe. In relativistic gravitation, timelines can diverge. Events that are separated by gravity experience time differently. The time period between cause and effect depends on where you are in space-time. Now consider the universe as a whole. On cosmological scales, gravity is not dominated by single objects, but by the collective mass energy of galaxies, clusters, and dark matter. Time itself unfolds differently in dense regions than in vast cosmic voids. The early universe, extremely dense and hot, experienced time very differently from the universe today. Processes that occurred in fractions of a second after the Big Bang shaped the entire cosmic structure we see billions of years later. In this context, the concept of time period becomes intertwined with cosmic history. The age of the universe is not a single, simple number that applies uniformly everywhere. It is a measure defined relative to a particular cosmic frame. Different regions, influenced by different gravitational conditions, experience the passage of cosmic time differently. The universe is not synchronized like a giant clock. It is a vast network of local clocks, each ticking according to gravity. This realization leads naturally into the final part of the main body, where we confront the limits of our understanding. What happens to time period when gravity becomes so strong that our current theories break down? What happens at the singularity of a black hole, or at the very beginning of the universe? Near a singularity, our equations predict that space-time curvature becomes infinite. Time, as we understand it, ceases to behave in any familiar way. The concept of a time period, something that repeats, may lose meaning entirely. There may be no next cycle, no predictable rhythm. Our current theories cannot describe this regime fully. This is where general relativity and quantum mechanics collide, and where a future theory of quantum gravity is needed. Some approaches to quantum gravity suggest that time itself may be emergent, not fundamental. In these views, time period is not a basic ingredient of reality, but a large-scale approximation that arises from deeper, timeless processes. Gravity, in this picture, it does not merely shape time, it gives rise to it. If this is true, then the journey we have followed, from pendulums to black holes, is more than a story about time measurement. It is a story about the origin of time itself. The simple act of measuring a time period under gravity may be revealing something profound about how the universe constructs reality. Even without venturing into speculative theories, one conclusion is unavoidable. Time is not separate from gravity. Every oscillation, every orbit, every heartbeat is embedded in a gravitational context. The time period you measure is a local truth, shaped by where you are and how space-time is curved around you. When you watch a clock tick, you are witnessing gravity at work. When you observe a planet complete an orbit, you are seeing gravity set a cosmic rhythm. When scientists measure changes in orbital periods of distant stars, they are listening to space-time itself. This understanding transforms how we see the universe. It replaces the idea of a rigid mechanical cosmos with that of a dynamic, responsive reality where time and gravity are woven together. The universe is not a machine running on a single clock. It is a symphony of clocks, each playing its own rhythm under the influence of gravity. As we approach the end of the main body of this exploration, the message becomes clear. The concept of time period in gravitation is not a narrow topic confined to textbooks. It is a thread that runs through all of physics, connecting motion, time, space, and gravity into a single coherent story. From the smallest oscillation to the grandest cosmic motion, gravity is the silent conductor, and setting the tempo of existence itself. And perhaps the most humbling realization of all is this: you are not outside this story. You are part of it. Your own passage through time is shaped by the gravitational universe you inhabit. Every second you experience is a local agreement between your motion and the curvature of space-time around you. Time is not merely passing. You are moving through a gravitationally sculpted reality, one time period at a time. As we reach the end of this long journey, it is worth pausing, not to stop time, but to reflect on how profoundly our understanding of it has changed. We began with something almost trivial, a swinging pendulum, a repeating motion, a simple time period that seemed fixed and predictable. And yet, by following that idea honestly and deeply, we arrived at a universe where time itself is flexible, local, and shaped by gravity. What once appeared to be a background stage for events has revealed itself as an active, dynamic part of reality. The most powerful lesson of gravitation is not that it pulls objects together, but that it binds space and time into a single fabric. Every example we explored, pendulums slowing on mountain tops, satellites aging faster in orbit, pulsars ticking in intense gravity, clocks near black holes stretching toward infinity, points to the same truth. Time does not flow independently of the universe. It responds to mass, motion, and energy. Gravity is not just something that acts within time. It helps define what time is. This realization should change how we see even the most ordinary moments of our lives. When you glance at a clock, you are not simply observing seconds pass. You are witnessing a local expression of space-time curvature. That clock is keeping time according to the gravitational environment in which it exists. Move it higher and it will tick faster. Move it deeper into a gravitational field and it will tick slower. The differences may be tiny, but they are real. The universe makes no exceptions, no matter how small the effect. Perhaps the most humbling aspect of this story is that there is no master clock for the cosmos. There is no universal now shared by all observers everywhere. Each object, each observer, each system carries its own time, shaped by gravity and motion. This does not make reality chaotic, it makes it richer. The laws governing these differences are precise, consistent, and beautifully interconnected. Nature does not demand that time be the same everywhere. It demands only that it obey the geometry of space-time. We often think of time as something that happens to us, something we move through passively. But physics tells a different story. We are participants in time, not spectators. Our motion through space and our position in gravitational fields influence how we age, how processes unfold, and how we relate to the rest of the universe. Even now, as you listen to these words, time is flowing at a slightly different rate for you than it is for someone standing at a different altitude or moving at a different speed. The difference is imperceptible, but the principle is absolute. When Einstein showed that gravity could slow time, he did more than correct Newton. He forced humanity to abandon the comforting idea of a universal timeline. In its place, he gave us a universe where time and space are flexible, responsive, and deeply connected to matter and energy. This insight has reshaped physics, technology, and philosophy alike. It has allowed us to build systems like GPS to understand extreme cosmic objects and to glimpse the limits of our theories. Yet despite all this progress, gravity and time still guard their deepest secrets. At the centers of black holes and at the beginning of the universe, our current understanding breaks down. Time period, repetition, and even causality may lose their familiar meanings. Somewhere beyond our current theories lies a deeper description of reality, one in which gravity and time emerge from something even more fundamental. The pendulum has not finished its swing. Yeah, and that is perhaps the most inspiring conclusion of all. Physics is not a closed book. The story of time and gravitation is still being written. Each discovery, each experiment, each new idea brings us closer to understanding how the universe measures existence itself. What began with a swinging chandelier in a cathedral has led us to black holes, gravitational waves, and the edge of cosmic time. So the next time you think about time, do not imagine it as a rigid, invisible river flowing uniformly for everyone. Imagine it as something alive, stretching, slowing, and adapting to the gravitational landscape of the universe. Imagine it as a rhythm set by mass and motion, a rhythm that changes from place to place, from star to star, from one edge of the cosmos to another. You are living inside that rhythm. Every step you take, every second you experience, every heartbeat you feel is part of a gravitational dialogue between you and the universe. Time is not simply passing you by. It is responding to where you are and how you move through space-time. The time period of your life, like every time period we have discussed, is shaped by gravity. And that is the final takeaway. Gravity does not just govern the motion of planets or the fall of apples. It governs the flow of time itself. To understand gravitation is to understand why time behaves the way it does. And to understand time is to glimpse the deepest structure of reality. The universe is not running on a single clock. It is composed of countless local clocks, each ticking to the rhythm of gravity. And together, they form the vast, intricate, and awe-inspiring symphony of space-time.